Let's start the recording. So before we start with the lecture and the quiz and all of this information, I would just like to remind you guys that next week will be your midterm exam. It's going to be a 1 hour exam and Saturday. So the second hour of Saturday will be your exam, or the last hour of our sessions on Saturday will be your exam. The hour before that, we will have a long revision. So all of us, basically, we will go through all the lectures, all the labs, any questions that you guys have about everything that we did from the start until what we will be doing today. And yeah, after that, you will be gathering in some classroom inside the university under the supervision of one of my friends, who is my colleagues who are teaching in Innopolis. And yeah, from there, if you guys have any questions, I will be available, of course, through Zoom. Most likely the midterm exam will be very simple, so it's going to be the same pattern of questions as the quiz, but more in depth. So basically, instead of just giving you true or false, I will just ask you how is this thing done, and you just answer in a small, what is called paragraph or small sentence, right? Let's wait a little bit for others to join because this is a bit of important information. Other than that, do you guys have any questions?
Is it possible to have this exam online because there is some probability I will not be in Annapolis and I cannot be presented?
So is it possible to do it online? Yes, maybe for like some, like what are they called? Exceptions. Yeah, for you, you can do it. Just open your Zoom and
Yeah, of course, if the phone camera is on, it's okay. Yeah, I think.
perfect, perfect. Yeah, then just
Okay,
do that
thank you
and
very
just
much.
scan it for me. Yep.
It will be the same time as we have the lectures, right?
Yes, exactly. It will be the same time. So basically, the first lecture of Saturday will be a revision. The second lecture will be an exam.
Are we gonna have a class on Friday? Because according to schedule, we're not.
That's a good question also. So what do you guys think? So basically, I think the schedule says, let me check the schedule again. The schedule says that we have only 3 lectures on Saturday, right? That's it, 24th, right? Do you want to do another lecture? So to take the lecture from 8:40 to Friday, just one lecture on Friday.
You mean 2 lectures on Saturday?
And one lecture on Friday. Yep.
Yes, I don't know.
Can you
I
please
think
repeat one more time?
Paul, maybe Paul.
I really don't want to do another lecture right before the midterm. And if we do a lecture right after the midterm, it will also be useless because you will not be paying attention. So maybe we should just move one of these lectures a bit.
On Friday, you mean?
Yeah, either on Friday or we send them to another week. So for example, next week, yeah, on the 30th.
Next week we have like only Friday and one lecture.
Yeah, so we can put it on.
I think it's possible.
Yeah, we can send it to the next week, right? Maybe next week on same time, Saturday, right?
Yes, do 2 lectures at the 1st of May, for example. Maybe so, it's like a exit.
Yeah, so basically the schedule for the next week will be 3. So basically just 2 lectures on what is it called, on Saturday. The first lecture will be just a total revision of all the content of the course.
It's about 24th of April, yeah?
I didn't hear you.
24th of April.
Yes, 24th of April.
Okay.
Yep, 24th of April. From 10:20 to 11:50, there will be a revision. And then you guys will have like a small break, right? After that, we should just get to some room inside the university. We will coordinate that with somebody in the university, and you will just pass your midterm there. After you finish your midterm, just scan your answers and send them to me either in Telegram or maybe preferably upload them directly through Moodle.
Okay, both variants are okay, I think.
I didn't hear you.
Both variants are okay.
Yep. Please don't upload your answers, of course, on the group. So basically, just send them directly to me. Some of you guys might do that. Maybe we should just move the third lecture from. Nice, great. Exactly, that's what we just discussed, Pavel. So basically, the third lecture of 24th of April will be moved to 30th of April. Let's write it in the group, right?
Maybe May, maybe 1st May.
Thank you. What is on 1st May? So basically 30th of.
30th is Friday. 1st of May is Saturday. We discussed before about the Saturday.
Ah, yes, then Saturday, yes. So basically the third, let's say, the first lecture of 24th will be moved to 1st of May. The time would be, let's say, at 10:20, right?
Yes, yes.
Yeah. Now that we have the the midterm done, for tomorrow, guys, you're gonna have to make your decision about the project. So as you know, the project contains like a very large part of the grades, and hence both lectures of tomorrow will be given only for the project. So basically, you will be discussing ideas. If you have something that you would like to pursue, maybe we can like find some new ideas that you can discover, or that you can just like work with, implement, and see its results. If it's a good one, you can publish it as a paper. If you have already like a small project, or as we said, as Farouk suggested, a Kaggle competition, just show it to me tomorrow and we can discuss how we can convert that into something that is acceptable for the final product.
Can I ask a question?
Yes, of course, go ahead.
So next Friday, the 23rd of April, we won't have any lecture.
Next Friday, the 23rd, let me check.
Yes, it seems no lectures at the 23rd of it.
Yep, there are no lectures.
Okay. And about the projects, we will discuss them tomorrow. Like you had some suggestions, if you want to ask you about some of them.
Yes, do you guys have any, so what we discussed so far is anything that is paper-like, so basically just some new idea in the field of computer vision. Even if it's not like super gigantically new, then it's still acceptable. Another project would be just to do, for example, label your own data set and create a object detector on top of that. So basically, another one would be contributing to any open source project that is already out there. There are many open source projects right now that, for example, give you some kickstarted or like get started code for doing, I don't know, object detection or something like that. And it would be nice if you guys contribute to such projects. Open source projects are always good for your resume. Another one would be to just completely have a published or like a deployed model that is doing computer vision on the internet. So for example, if you have a company or something like that, and you have a working version of your software that is online, then we can accept that also as a final product.
Can I ask, can a project be a kind of a tutorial or how-to sheet that will explain how to do the CI using GitHub Actions for machine learning, and especially CV and GPU pipelines?
Yes, if the content is difficult enough, then definitely.
Okay.
So the content should not be something similar, for example, to our labs. You know, our labs level is very easy, it's very basic. You should try to do something a bit more difficult than what we are doing in the labs.
Yes, the point is to explain how exactly GitHub Actions work and how can you approach GitHub Actions. So they have their own syntax and tutorial on the syntax. It's okay. But the point is, if you have your own private libraries if you have multiple private libraries, you cannot have the single SSH key and stuff like this. They don't have GPU workers, so you need to have your own GPU worker. So you need to set up a worker, connect it to GitHub, and blah blah blah, and set up all the pipeline. How to do PyTest with machine learning pipeline and stuff like this. I'm just currently working on it, so can it be? Like
yes, this looks kind of interesting. Yeah.
Cool.
We can discuss this a bit more in more detail tomorrow, right? So for now, the first thing we will be doing is the revision of what we have done in the last lecture, and then we will open up the quiz, and you guys just go ahead, answer the quiz in, I would say 10 minutes this time. So it's very simple. Let's make it 10 minutes.
Okay.
And after that, we will answer the quiz together and start the new lecture, right?
Looks great.
Nice. Do you guys have any questions so far about the previous lecture that you would like to cover before I get started, or should we get going?
I have an important question.
I have some.
Yes, go ahead.
Go ahead. Go ahead.
I have some. It's a general question about Colab. Is there an easy way to run Python scripts on Google Colab? Like if you have a project with many scripts on PyCharm, for example, or something, can you run on Colab somehow?
Yeah, I got you. Just upload them to GitHub, for example. You have your own repo in GitHub. And then the first line of your Colab link would be git clone your GitHub repo, then like %cd your GitHub repo's name, and just like the thingy, like what is it called? Exclamation point,
yes,
Python, run. Yeah?
Yes, okay, thank you.
I think this is the easiest way.
Imad, can I ask a question about what we have discussed in previous time? Actually, and on Friday and on Saturday is about what we have discussed with you about the YOLO 4 and YOLO 5, and you actually said what your colleagues from the industry and from the academy said what there is a model which even faster and even more accurate than YOLO family, like the set to for now. And you said what you maybe you will have opportunity to ask for them, introduce this model to us. Have you done it? Or maybe not?
I have done it. I have tried it. I have trained it. It's very simple to train it. I really like the simplicity of the model. But according to the MAP scores on this project that I tried, YOLO V4, YOLO V5 actually gives a lot better results than this. So in here, the best MAP score that I got was 66.7, 0.667, right? And with the small version of YOLO V5, we arrived to even 81, 0.81. So
even like, small one.
Yeah, using the small one, yeah. So yeah, in the data set that I used contains a lot of images, so that's why the task is a bit simple. So it's a very constrained task inside the industry, and like the scenario that we have is very well done or well defined. That's why the accuracy is very high. And yeah, even YOLO V5, the small model, was able to give much better results. So far, if you guys want me to show you this, well, yeah, we can see it.
No, if you think it's like not worth enough to spend our time, and maybe like it's you have actually better, I think it's like just not mandatory. If you will have time, maybe
share it with you guys and show you, because it's very simple. And maybe the problem was actually in me. I didn't really spend enough time to find hyperparameter tune it and stuff like that. So basically, I just use the default parameters. Yeah, and you guys might explore it in your final project if you want. Why not?
Okay, thank you.
So let's go to the object detection lecture, and just a quick revision before the quiz. For some reason, my laptop is screaming. Oops. I don't know. Let's just start. So in the last lecture, we spoke about object detection models. We've seen what object detection is and how it's performed, and we proposed like a very basic model to do object detection. After that, we started speaking about the RTNN family, and we spoke about the first model of RTNN, so the RCNN model. Then we spoke about fast RTNN and how it improved over the RCNN implementation, and then we spoke about the faster RCNN, and we saw how they improved the speed by removing the selective search algorithm, right? After that, we also mentioned a little bit the mask RCNN architecture, and today we will be going into more detail about the mask RCNN architecture. The final part was speaking about YOLO and Detectron, which are like the two biggest libraries or families you can think of in terms of object detection. We saw how YOLO v3 works and what are the steps in there. And most importantly, we saw why are the, for example, what are they called? The number of filters in the last layer, last convolutional layer that comes before a YOLO detection layer has to be number of classes plus 5 times 3. Object detection. So basically, object detection allows us to get the following results. So basically, instead of just classifying an image and attributing a label to the whole image, now we are attributing multiple classes into the image and finding where these objects are. So for example, in this case, we have 2 cats, hence we have, and we have 2 boxes for each cat, right? Each box is defined in a different manner, depending on the algorithm you will be choosing. So we have seen that there are mainly 4 types of doing this, of defining this box. The first one would be the top left corner with the coordinates of the top left corner and the coordinates of the bottom right corner. Another way would be the center point coordinates and the height and width of the bounding box. And there are 2 versions of this of these 2 methods, which use either the real coordinates or the scale coordinates or the normalized coordinates based on the height and width of the image. We saw that the applications of object detection are endless. First, we can see vehicle counting, which is a combination of object tracking and object detection. We will be speaking about object tracking and object tracking in the next layer, next lecture. So basically, after the midterm, we will be speaking about object tracking and other algorithms for that. A good way, another application area is facial detection and recognition. So basically, detecting where the face is made using object detection. And then we saw that this parking lot monitoring application, and this was the lab part of our session, right? Remember, we took this data set from RoboFlow, which is an open, which gives us the access to an open data set, and then we just used their code to basically train, I think, a YOLO v5 model, as I'm not mistaken, if I'm not mistaken, right? Yeah, we used a YOLO v5. We trained the YOLO v5 model to do this, right? And then we said that the basic method that we can use for detecting objects is to just slide a convolutional classifier on the image. So basically, we start at this place and just classify if this place, if inside this place we have a cat or a dog or something like that. And then we continue sliding it through all the patches, for example, of the image. One problem of this model is that it will have not infinitely, but a large number of convolutional applications. So basically, every group of pixels like this will have a convolutional operation, and then we just move one pixel and then apply convolutional again. So this method is very computationally expensive. We saw that one way of improving it would be to just rescale it to a small, downscale it to a very small size, apply the convolutional classifier on patches inside this image, and then the areas of interest will be increased, and then we just continue, what is it called? Refining the area of interest again and again by using the classifier. Another method to reduce the number of convolutional operation we use on this image would be to use something called the selective search algorithm. So the selective search algorithm proposes to us a different parts of the regions, different regions of the image, which are interesting, right? So the word interesting means that they have a lot of action going on, for example. Or another algorithm might give you, like, for example, the pixels or the areas which are most similar, for example, right? So he would take a look at this area and say that this area is a whole object and it is the sky, right? And then it would come to this place and say that this red part is something interesting. It might combine it with this white part and say this is another, these two together might contain an object that is interesting. So this is what selective search does. We spoke about intersection over union, which is a metric for evaluating object detection models. We saw that the higher the intersection between the predicted box and the ground truth box, the better the prediction is. And the bigger the union compared to the intersection is, the worse the predictions are, right? So basically, the perfect example would have a one intersection and one union, and basically what. So let's speak in terms of pixels. For example, we have 500 pixels in intersection and 500 pixels in union, and the IOU would be 1. We spoke about non-maximum suppression, which is an algorithm that is applied after our model. So the basic model that we just described suffers from a big problem, which is overlapping predictions. So basically, once we make the detection in this area, if we shift this box with just one pixel in, for example, the right direction, the classification would be the same, and then we would detect another box, like literally just one pixel away. So basically, we'll be having a lot of overlapping bounding boxes. And to solve this, we use the non-maximum suppression algorithm. This algorithm works very simply. We find the box with the highest confidence, that was predicted with the highest confidence, and then calculate the intersection over union with the other boxes. If we have other boxes with high intersection over union with our first box, we just remove them from the predictions. And then we continue iteratively just finding the next box with the highest confidence level, finding all the other boxes with the high intersection over union with it, and then just removing them from there. You can find the steps described in this algorithm here. Now we speak about the first real algorithm used for object detection. And to be honest, it's not very much different from what we just described. So from this algorithm, right? So basically we will have an algorithm that looks for interesting areas inside the image. And then we send these interesting areas to a convolutional classifier for classification. So this is what's happening here. We take the input image, we extract region proposals. The algorithm we used in this case is called selective search, and it proposes around 2,000 boxes inside one image, right? Then we take this region of each one of these regions of interest, we wrap them into our desired size. So it doesn't matter what the size of the input is or what the size of the extracted region is, they will all be mapped into the same size and then be sent through a convolutional classifier. After this convolutional classifier, usually there is, what is it called? So basically the final layer is a fully connected layer. After that, we will be building a SVM classifier for each one of these classes, right? So either it's an airplane or no, person or no. So basically it's going to be a one versus all SVM, right? In a disconnected manner, there will be also another part which will be predicting the coordinates of the bounding boxes of the object that is inside the what is it called, this area of interest. This is just some more details about how selective search algorithm works, but we saw it in like in a separate article. Just we went through more details about it. Right. The main problem of RCNNs is that in training time, every image will have 2,000 classifications, right? So you will have 2,000 back propagations for every image, and this is a lot. Every time you will do this calculation, it will take a lot of calculations, right? And the inference time was around 47 seconds. Waiting 47 seconds to perform one object detection on a single image is quite infeasible for industrial applications. At least for research, you have more time, but for industrial applications, 47 seconds is not an acceptable period. And another big problem is selective search algorithm is not data set specific. So basically, the algorithm that we will be using for generating the regions is not depending on our dataset. So it doesn't matter what type of objects are we interested in, what are the sizes of the objects that we are interested in, are the images that we're using medical images, real images, paintings, or any of these things. Doesn't matter what they are, we will be using the same algorithm for selecting these or for proposing these regions of interest. And as we know, there's no solution that fits everything. So this solution is quite bad, right? It gives bad results. The fast RCNN model was a small improvement over RCNN. And the improvement was the following. So basically, instead of sending the whole, sending each region through the CNN and then sending it for classification, they decided that we will send the image, the whole image, just once. We get the feature map of this whole image just one time, and then apply the same selective search algorithm on the input image, find these proposal regions, right? The 2,000 proposed regions, and then map them directly into where their location would be inside the convolutional feature map. So previously in fast RCNN, what we did is we take this image, send it, take these each one of these regions and send them to the CNN to extract the feature map and then send it to fully connected layers, right? In this case, the feature map is extracted only once, and every region we will be just searching for its corresponding part inside the convolutional feature map, and then the convolutional feature map will be resized and just sent to fully convolutional layers, and then classified and applied bounding box regression on it. Again, classification is a very simple task, and bounding box regression is just predicting the coordinates of the, for example, this point and this point. Let's say this is 3 by 50, and this is 140 by 300, right? This ROI pooling layer, it's very similar to max pooling, but the main difference is that it will take any input shape or any input size and map it to the same size. So it doesn't matter what the size of our region of interest in here, their mapped convolutional feature map will always be the same size. And this is very useful because the next layers will be fully connected layers, and they always require the same size input. So this is just an example of how we are finding the area of the ROI proposal inside the feature map. So it's just direct mapping. And then we apply ROI pooling on that region. The main problem of fast RCNN, so basically you see that the training is much better now, and the inference time also is much better. But the main problem here is with including the selective search algorithm, the time is 2.3. When we don't include it, so we just basically imagine that the proposed regions already existed, and we just apply the part of fast RCNN, then the time becomes 0.32. So here we can see that the big problem or the most time consuming part of the algorithm is the selective search. And as you can guess, faster RCNN proposes a solution to fix this problem and replaces the selective search algorithm with a neural network. So this neural network now, so as you can see, this part for classification and object detection is the same. So this is the fast RCNN architecture, but the feature or the regions of interest are no longer fed through the selective search algorithm, but now they are fed through the region proposal neural network. So the region proposal neural network looks like this. We send the image to a convolutional neural network. So in this case, we have BGG, but newer versions of faster RCNN tend to use something called as feature pyramid networks. Feature pyramid networks are a bit better. So they're very similar to what we will be speaking about in this next lecture on UNet, but they are a bit more rich in with the kind of information they retrieve or the feature maps that they retrieve. So basically, we will just have a backbone CNN that will give us a feature map like this one. And in every one of these pixels inside the feature map, we will be applying an anchor, right? Now let's speak about what anchors are. Here we come, for example, to this pixel, pixel A. This is what's interesting us. And we would like to see if inside pixel A, or pixel, if pixel A is the center of an object inside the image. So what we do, we take this pixel inside the feature map, find its location inside the original image, and basically put three types of anchors on it. So the first type of anchor is the large anchors, the second type of anchors is this medium anchors, and the third type of anchors is the small anchors. Each one of these anchors contain three sizes. So basically 1 by 2, 1 by 1, and 2 by 1, just to be able to detect objects in different sizes and different ratios.
A question.
Yes.
Anchors used somewhere outside faster RCNN.
Yes, they are used in lots of architectures currently, and some newer versions allow you to even train the size of the anchors and train the to just basically train the size of the anchors, or like find better patterns to detect or to what is it called, select the sizes of these anchors depending on the sizes of your objects, basically. So in these cases, you see that these sizes are the same for all different data sets. And of course, this is a bit of a problem. So if you want to train basically the sizes of your anchors, you can do that in different architectures such as PPYOLO. I remember it allowed you to do this. Does it give better does it give increased performance? So what I saw was that it doesn't really give anything more interesting than YOLO v4 or YOLO v5. Each one of the anchors that we just spoke about will contain the following. So basically we have K anchors, usually it's 9. We put them in here, and then we take this region or the region that they are highlighting and send it basically through a fully connected layer, apply it for classification score, and try to do a basic bounding box regression on it. The classification layer has 2 k-scores, and the coordinates has 4 k-scores. This is very logical because we have 4 coordinates for each object, and since we have k anchors, then we have 4 times k. This one is a bit tricky since the 2 times k in this case stands for whether there is an object or there is no object, right? So basically, we will not be just detecting whether there is an object, right? So if we use binary classification, which just uses one value, it will tell you whether there is an object or no. If you use this formulation of having 2 pixels for each one of these classes, for the yes class and for the no class, then there will be some cases where neither of these classes will be activated, right? So in the case where you have high overlap, you will be putting the, the yes pixel on, or the yes class on. And if you have the, the very, very low overlap or zero overlap with any object at all, then you will be turning on the no class, right? And everything in the middle, so for example, if we have just a 50% overlap, in this case, we don't classify this anchor at all. So basically, we completely ignore it. This would allow you to have a more let's go it a little bit. So basically, the output would give you high activations in this area for the yes class, and then high activations for the no class surrounding the object, right? But all of this area will not have any activations, neither yes nor no. So it will be completely low on the output of this classifier.
There is any disadvantages because of that?
Yeah, it does give better performances. So basically, it was tested and gave better performances. That's why.
No, disadvantages. It has disadvantages.
Does it have the same function? Maybe it has a bit more calculation, but it's not really that big, right? So it's the same thing. It's not really that much more expensive, just a little bit. And it's easy. Compared to the other parts, it's not that more expensive now. Again, just for a quick recap on the faster RTNN. So first, we send the image through a backbone. We get a feature map. The feature map will later on we will apply a set of anchors on every pixel inside this feature map, and then every one of these anchors will have the following: either classification or regression. They're both at the same time, right? After we get this, we will have our proposed regions. How do we get the proposed regions? So basically, we go through the image. Every time there is an anchor with high yes score, we say that this is a region of interest. And then we take the regressor output just to find where the object is put exactly at. Send these regions to the fast RTNN architecture and then perform the same task of basically classifying. So in this time, we are classifying the class of the object and not just whether there is an object. And in this area, we are classifying, we are regressing the bounding boxes. A quick recap of all the RCNN family. So we take an image of RCNN, we take an image, send it through the convolution, send it through the region proposal algorithm. Every region will go through the deep CNN, and then will be sent to an SVM classifier and an object and the bounding box regressor, which are independent of each other. The fast RCNN improved it. It uses the region proposal algorithm, find the regions inside the image which are important, send the whole image just once through the CNN, and then every region will just find its mapped feature map, send it through ROI pooling, and then for classification and bounding box regression at the same time. The faster RCNN improves over both of these architectures by completely removing the region proposal algorithm and replacing it by what is called region proposal networks. The rest of the architecture remains the same with fast RCNN. The mask RCNN architecture is the same as faster RCNN, but it only adds a small part for predicting the mask. We will speak about what is the mask and what it looks like, but basically it's just a binary image. You can think of it as just a binary image with 1 in the places where the pixel is activated and 0 where the pixel is supposed to be a background. We spoke about what Detectron is. So basically, Detectron is only a library that provides us several implementations of the algorithms that we just talked. So basically, the RCN family. And some of the algorithms it has. So for example, here we have DenseNet, I think. This one we have image segmentation. We have here key points detection. So basically, we're trying to detect the key points of the human being. So basically, we're finding the pose of the human being. And here we have just object detection with segmentation coupled together. So you see the difference between these objects is every single pixel in this area is segmented, whereas in this image only the pixels which interest us are highlighted. We spoke about the YOLO before V3 and before architecture, so basically they're kind of the same, and said that they provide us with 3 levels of detection. So the first difference between RCNNs and the YOLO family is that the YOLO family does the object detection directly, unlike the RCNN family, which finds first the regions and then classifies them. In this case, we have 3 scales of predictions. So we have the third scale, which tries to predict or tries to detect objects of small size. We have the in medium scale, which finds objects of medium size, and then we have this small size, very small size, which tries to detect objects of large size, right? On each one of these levels of detection, we will have the following. So basically, we will have a feature map. For example, in this area, it's a 13 by 13 feature map. Every single pixel or every single index in this coordinates or in this feature map contains the following. So remember, this feature map is a 3D object and it contains a lot of channels. And here, every single one of these contains the following information. It contains the information for 3 boxes. Each box contains the following. The objectness score, remember the objectness score, whether there is an object or not, and the bounding box coordinates of this object, and the class of the object. All of this is done at the same time, unlike RCNN, which does only these things first and then predicts the class later on. So yes, this is the content of one of these boxes, and YOLO v3 and YOLO v4s have 3 boxes in every single one of these pixels. Hence, the formula becomes of the number of filters formula becomes number of classes plus 5 multiplied by 3. So this is for the number of classes. So we have a, let's say, a pixel, not a pixel. We have a value for every class, and then we have 5 values for the objectness score and the bounding box regressions. Multiply them by how many boxes can we detect on a single pixel or on a single coordinate.
But may I please say one more time why we have 3 boxes one time? Is from what?
Yes, remember what we have here in anchors. Let's just come back here. So here we have 9 anchors, all applied to the same pixel, right?
Right.
In there we have 3 anchors for every scale. So basically we have an image that is looking for small objects, right? And that image or that feature map contains 3 anchors for every pixel. Another feature map looks for medium objects, and each one of its coordinates or its pixels contains 3 anchors. Another one is made for large images, and each one of its pixels contains 3 anchors. So they are corresponding to these 3 anchors in here. So basically, we have 3 types of anchors, either laying down, standing up, or a rectangle with the same sizes.
Can I ask a question?
Yes.
About the same image of anchors? As I understand, we sweep the anchors inside the feature maps and then do this anchors of 3 sizes. So it's kind of the same idea as sliding window. Only
yeah.
like. Okay, thank you.
Yeah,
Can I also ask a question about the 2K scores here?
Here, yeah.
So we have an independent, basically, where is this used in faster RCNNs?
Here, that's a good question. It's used in this area, right?
Oh, okay.
You see the region proposal network. We go into more detail about the region proposal network. We see here region proposal network sends the image through a backbone and gives us a feature map. And then for these feature map, we will be applying the following: these anchors, right? After the anchors, we will have what is it called? The classification and the bounding box regressors.
Yes, okay, thank you.
And here we see just a little bit more explanation about what the anchors are. And then we go a bit more in depth about what the anchors really are doing. So here's just where the anchors are made. Each one of these anchors, how it's working. You see the structure of the thingy.
Yes, thank you.
Nice. Just a small comparison in here. This part is exactly similar to what YOLO v4 is, YOLO v architecture is doing. The main difference is here. So RCNN, yes, RCNN family first detects whether there is an object or not and solves it, and then does the classification in a separate neural network. Whereas the YOLO VX architecture does, it detects whether there is an object, detects its coordinates, and its class at the same place. So the same neural network looks at the image only once. This is what the name YOLO comes from. You only look once, right? So basically,
For these box values like coordinates, class scores, each of scores has a group of weights, right? Or these weights some kind of intersects with each other.
what do you mean each of these scores are? Yes, so for example, this pixel requires a certain calculation. Basically, they're all calculating on the same feature map, but they give you different, so basically they give you different weights. Different weights give you these different values.
But coordinates also have separate, completely separate weights, or they also intersect with class scores weights.
You mean, for example, the weights for this pixel and the weights for this pixel?
Yes.
Yes, they are shared. Basically, it's the same model that is sliding through all of them.
But here's any unique part for each pixel.
I didn't hear you.
Any unique neurons for unique pixels, or it's completely shared?
All of them are shared. Every pixel has the same weights that find these values, right? So basically, we start here. These each box will have its own what is it called, calculations or size of kernels, but in the end, they all give you just one value, right?
I'm not completely sure how boxes interact with each other.
Boxes, they don't really interact with each other, right? So basically, you go to this pixel and try to look for objects in this pixel. Then you go to another pixel and try to look using the same weights for objects in this area. But there is no relationship between the pixels in whatsoever.
Okay, I understand. Thank you.
Yes, I think that's it. So basically, as we said, there are 3 scales of classification or of object detection inside YOLO V3 architectures. Each one of them is responsible for a different object type. So
Can
now
I
that
ask
we have finished the
a
revision,
final
do you guys
question?
have any questions?
Yes, can I ask a final question? What is the data sets that are used to like benchmark this object detection model, and how many classes do they have?
Yeah, I think there are lots of different data sets. Let's check them out right now. What is it called? Let me share the screen again. There you go. Not here. Let's no, sorry, go back. Okay. There is coco.names and it has the following. So it has 80 classes. Remember the something.names file contains the names of your classes. Yes, we have the open images dataset of Google, which has 601 objects. And here we have the VOC, which has 20 objects. So I think these are the main benchmarks that we can find. There might be other benchmarks, but I think these are the most important ones. So let's see what is this one benchmarked on. Yeah, this one is the benchmarked on Coco dataset. Yeah.
Okay.
Nice. Next question. Do you guys have any other question?
I have a question.
Yeah.
Why do we use different scales in YOLO? I didn't catch very well.
Yes. This is a great question. I didn't explain it correctly. So I should go a bit more detail. Nice. So far, let's just focus on this area, right? So we take a big image, then we send it through some convolutions, some max poolings, some all of these operations. The size of the output of every one of these operations will shrink, right? They will decrease.
Yes.
So the person who asked the question, please continue with me like a conversation, right? So basically, every time we send it through a layer, it will decrease in size. In here, we will get to an image of size 13 by 13. You see? So, for example, we started by 450, 416, and we got to 13 by 13. In here, if you had some very big objects inside your image, even if you downscale it into a 13 by 13, you will still be able to find traces of these objects, right? Nice. Now, so basically this one is responsible for detecting large objects. But if you had very tiny objects inside your image, and you keep on downscaling, 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 then, for example, it was in this area of let's say 10 by 10 pixels. This area will be mapped into less than 1 pixel inside this image. So it will not be able to be detected inside a smaller scale, right? Hence, what they do is, first they upscale this feature map and then combine it with the previous feature maps, right? And then continue upscaling and upscaling, just like convolutions and upscaling, until you have a bigger, let's say a bigger object or a bigger feature map. Inside this feature map, you can find mid-size objects, right? So basically, it's a little bit bigger than this one, not super big. Hence, the information about smaller objects, like medium-sized objects, would still be detectable inside this area. Of course, large objects are also detectable in this area, but why did it? Somebody was annotating. Nice. Thank you. So basically, yes. So basically, this area will contain the anchor sizes will be more suitable for mid-sized objects. Did you get this?
Yeah, yes.
So if you apply a 3 by 3 anchor in here, it will give you a corresponding big object in this area. If you apply a 3 by 3 anchor inside this pixel, for example, around this pixel, it will give you a medium-sized corresponding object inside this image. Again, what we will be doing, we will take this feature map, upscale it, combine it with the previous one, and then send it through just a couple of convolutions. And now we have a bigger image that will be able to give us more information about even the smallest of objects.
Thank you. I understood.
Thank you. Any more questions? Quiz.
Please.
Imad, could you please quiz for listeners also? I mean, PDF.
Yes, exactly. I will.
Thank you.
Please focus very well on the quiz questions. I want you guys to get as high of grades as possible because the grading of the final project will be very tight. So use the quizzes and the midterm for your favor to get as many values as possible, right? How can I extract it? How can I extract the quiz? Export maybe. Ooh. Oh, okay. I can just remove the answers and send it to you guys. Yes. For the what are they called? The free listeners who can't have access to the quiz, you will find the quiz in the chat. It's a TXT file. Let me now go ahead and open it for the students.
I have a question.
Yes.
About yellow. So we have like a big object detector. Can we like somehow optimize or speed up the model, not predicting in the region which we decided this region is dedicated to some object, and we can like avoid this region and predict in other places. Will it speed up or increase somehow accuracy?
It will speed up, but it will reduce the performance. Imagine this scenario.
Because like some object can overlap each other, yeah?
Exactly, yes, like this.
Okay. Thank you.
So basically, one of the anchors will find...
It's funny because you're doing background and this object you are showing is like invisible.
Oh, sorry. Let me... true. Let me remove the background.
Oh, it's okay. I get the idea. Thank you.
Yeah, like this. You see? So
Yeah,
basically,
yeah.
the horizontal filter, horizontal anchor will detect this one. The vertical anchor will detect this one. And if there was another one, you'll be able to detect it using the other anchor, right?
Okay, thank you.
Let me just open it for you guys. And instead of giving you just 10 minutes, I will give you around 14, right? Let's open the quiz around 85, 58, and close the quiz right after. We have 19, 14, huh? 1910. Is it now visible?
No.
No.
Should be. Try to refresh.
Yes.
Oh,
Right
yes.
now.
Nice. So I think it will open after 1 minute. So go ahead if you guys can answer. I think the questions are already in the chat. Please don't copy from each other, and try to answer it on your own. And right after that, we will be answering the questions together in here. Just make sure all of them are ready. This will not be available on Friday.
Sorry, for me, the test is unable. I don't know why.
Yeah, it's still enabled. Now it's yes, now it's able.
Oh, okay.
Now just go for it, and you will be able to do it. Just refresh. I'll send the questions also here, just so those who are not in the chat. But please tell me that the does not have any answers. Right, no answers. Nice.
It's a final countdown. You are muted.
Yeah, we didn't do the countdown, guys. Sorry. Next time.
Why so?
I forgot that the quiz was this fast. Next time we'll play this song, right?
Imad,
Mm-hmm.
is it possible? Could you please how to say we are not able to review our quizzes, like we cannot check the results, and so could you please turn on this functionality?
You guys cannot see the results of your quiz?
We can see
Yes.
results, but we cannot see
The
in which questions we
questions and
made
the answers.
errors,
You
mistakes.
can see all the scores.
Yeah. I was playing around with some features, so probably that's why. Let me just bring it back, you guys. Let me see. Now is it visible?
Yes.
Yes.
Nice. Let me. Why can't I check the answer?
Please do the same for the first one.
For the first one also you can't see it.
Yes, and even the grade.
You can't even see the grade. Okay, let's just go through them quickly, right? RCNN object detection requires performing which task?
Both of them.
Both.
That is show. The region proposal step in RCNN uses ROI pooling with
No.
That is show. So basically, the region proposal step in RCNN does not use ROI pooling. ROI pooling was introduced in the next version of faster RCNN, right?
Yes.
Fast RCNN uses selective search to find 2,000 proposals. So far, yes, this is correct. This is a fact. How are these proposals later classified? Either we find their mapped region inside the feature map extracted by the CNN, or
Stop here.
we pass each region through the CNN, or we send them through the region proposal map.
First one.
First one, great. ROI pooling always gives the same size output.
Mm-hmm.
ROI pooling takes the max of a region in the input and maps it to a single pixel in the output, similar to max pooling, right?
Mm-hmm.
Now the question is, ROI pooling also has a fixed size kernel that passes through the image as max pooling does.
It's not true.
False. So basically, we don't define any kernel size. So for example, 3 by 3 and stride equals 4. We don't define these things in ROI pooling, we define the output. Faster RCNN still uses a selective search algorithm, but doesn't send each image or each region through the CNN.
It's not true because we have a region proposal network now.
Exactly. So this is fast RCNN that does this task. Faster RCNN does not use selective search at all. Faster RCNN provides the regions of interest using selective search, SVM classifier, greedy algorithm, or RPM network.
RPM network.
Yeah, I hope nobody chose the SVM classifier.
It will be funny.
I would quit the course. RPN finds the location of objects by sliding K anchors on selective search, the convolutional feature map, or the input image.
Feature map.
Yes, it slides it through the convolutional feature map. Next. Detectron is a new paper that presented a new architecture for object detection different from the R family of RCNNs.
No, it's a framework which contains implementations of most of the RNN family, and also the mask RCNN implementation.
Or it's a library, not
sure.
a paper.
It's a framework.
Yeah,
Yeah,
it's library framework. You can think of it how you want. But basically, it's just code.
Yes.
Jolo also follows the same pattern of proposing the regions of interest and then classifying them similar to the RCNN family.
No, it's not true because there is no when. We at the same time propose regions and classify them.
Exactly. Yay, fish the intent. Not yet answered. Answer saved. Answer saved.
Matt, you didn't answer several questions. You get a bad mark.
I got 5 out of 10. Nice.
Almost correct.
So basically, this is what you guys see, huh?
Not exactly this, but I mean, in terms of results, but yes.
Ah, okay, got you. I hope you see better. Let me just now check the results of the quiz.
Yeah, Matt, for listeners, actually, the questions a little bit different.
How are they different?
Yeah, there are some questions from our first quiz about Lime, blah, blah, blah.
I extracted the first quiz.
It's no, it's not all questions, but some questions from first quiz, some questions from this quiz. Yeah, really? No, it's okay.
How? I think there is something wrong with the extraction. It's not my fault. I extracted directly. Nice. So here are the results. You guys can't see the screen, right?
Yes, we can. We can't. No,
yeah,
yes.
overall, you guys did a good job. So basically, I see that there are lots of 10s, lots of 9s, lots of 8s, lots of 7s, lots of 6s, and a couple of 4 and 5. So that's not bad. That's still good. Much better than the first quiz. I would ask you guys to maybe try to focus a little bit harder, ask a bit more questions before in the review, and try to get more in this area of 8, 9, and 10, guys. Okay?
We will try.
Nice.
Could you please make the first quiz also to be able for us to check?
Yes, I will do that right now. For today's lecture, it's going to be very simple. It's going to be very easy. I will try to make it very quick and easy one, just because I don't want you guys to have a lot of content for your next thingy.
Okay, Ahmad, I have a question before we start this lecture.
Yes.
It's a little bit general, that's why I postponed till after the quiz.
Yes.
About data sets, when we are trying to train for classification or for object detection, does it, is there a difference between the type of data set or type of features I provide in data set between if I want to train for classification or detection, or doesn't matter? Like, I mean, in sort of kind of background, kind of, it doesn't influence at all.
Yeah, it doesn't influence. Basically, image classification would be much better because you would provide it the exact frame of the object, and that exact frame of the object will be sent for classification. So basically, the classification would be much better on object detection. But if you're going to be doing classification where the objects you are trying to classify inside the image is very small, and basically the image contains a lot of other information, then the classification would be more difficult. But basically for object detection, even if the object is inside a lot of other objects, then it doesn't really matter. You're still going to be able to find it. But for classification, it's a bit more difficult if the object you're trying to classify is not the main part of the image, right? So if you're trying to do only classification without object detection, try to make your object that you're trying to classify the main part of the image. And if you're trying to do object detection, then it doesn't really matter.
But also about the training data set, it doesn't matter if I'm like providing training pictures with like white background or like blank background, or
it will help it definitely if you have white background, it will definitely improve the results or the accuracy of the object detection. But yeah, you can just completely ignore it also.
So in general, doing customized data set is much better than like collecting data set.
Yes, yes, yes. For example, one might, let's take an example of one of the projects we worked on with Profectus. So they're basically trying to detect hard hats and vests in construction sites. We have our own data set that we collected from our clients already. We train the model on that, and then we send the model for the deployment on this construction site. But the model will not be performing very well on that construction site for different reasons. For example, the colors of their hats are different. The distribution of the people are different. So for example, there are lots of Asians, or there are lots of Black people, or there are lots of other races that were not included in our training data. So as long as, well, as much custom data as you have in training, so the more custom data you have for training, the better.
Okay, understood. So like the more custom and the more wide for differences, like
yes, exactly.
in classes.
Mm-hmm. Хорошо, we go for image segmentation. Now let's start the second lecture. I hope that your brains are not already too saturated. You still can think, guys? Are you guys
yes.
still?
Nice. Yes.
Because we had today like a job.
Job fair. Nice. It's very
yes, important. This why we kind of.
Did you guys find something related to computer vision in there?
Only a few like companies provide some information about it. That is, and even a few which provides the data science positions, we also provide, for example, not with CV. It's not good.
For example.
Come on, Ali, we have CV.
Okay, you're one of the best because you have a position.
No, I think there will be lots of more opportunities coming around the summer. So stay
you think so?
open to other opportunities. Yes.
Thank you. We will wait.
For example, Provectus, they were not in the job fair.
No, it was Provectus was here.
Provectus was here, and they didn't propose anything for computer vision.
No, I mean we had a position.
No, I think
we had plenty of position. They just not presented it specifically
yeah. They will
because
here around the summer. There are other companies like Own also. I remember it's a good one. There's Yandex. All of these companies are there, you know.
Yandex not presented.
Yeah.
Own also not presented.
Own doesn't exist anymore.
They died.
Exists. It exists. I'm working here.
But that's okay. That's okay, guys. When the summer comes, you should be more ready for these opportunities. The most important part is that you should at least have some project to present, right? It's very important for you guys to have at least a paper or some good project that you have worked on, a big project, hopefully. The learning outcomes are for today. So we'll basically be speaking about autoencoders, variational autoencoders, and how can we use such models for segmentation. Later on, we will be speaking about what segmentation is, and we will be speaking about what some models in segmentation are, right? So let's start with what is it called? Autoencoders part. A very important thing that you guys understand, or terminology that you should guys understand, is feature extraction. What feature extraction is? So previously, what we used to do with images is we used to take the input, and then using some specific algorithms, we extract some features from these images and then send them for classification, for example, SVMs or something like that. So basically, SVMs don't understand an image. You can't input an image directly to the SVM, and you should be able to extract some features from that image, convert that into a latent space, or what is it called, a vector form information, and then send it for classification using any model that you guys know, SVM, based classifiers, or something else. Deep learning, on the other hand, does both tasks of feature extraction and classification at the same time. The feature extraction, let's think of it as two steps, a two-step process. The first one is the feature extraction, which is done by something called as an encoder. And the second step is done by a classifier. Usually the classifier is a model that is completely fully connected. So it does not contain any convolutional features or convolutional layers or max pooling or something like that. The classifier should always be just linear, what is it called? Dense feature maps, dense layers. And the encoder in most cases will contain only convolutional layers. And the final layer would be a flattening layer. But in some models, you can find that the encoder contains still some, just like one or two extra fully connected layers. A term that you might already be familiar with, at least for the guys who are in Master of Second, is autoencoders, right? So basically, autoencoders, they take an input image and they try to reconstruct the input image. So they are a type of feature extractors. So basically, this encoder is a feature extractor, but one that is not a supervised feature extractor. So it's not extracting features useful for classification or predicting the label, but it's classifying or extracting features from the data directly as it is. As you can see in here, so we can consider that the input image itself is our data or our label. So in this case, the label is exactly the input image. The decoder is the part that will be mapping the encoded space or the latent space or the representation space from a vector form into a image back again. There are some architectures which, for example, mostly after the encoders, you should have a flattened array, so a vector. But in the future architectures that we will be speaking about, they tend to remove completely the part where we use fully connected layers and keep only convolutional layers that will give you a convolutional feature map in here. And basically, we'll be sending it through the decoder and augmenting it again. What autoencoders do is the following. So basically, they take an image, extract some features. So for example, like this one, in a vector form, and then send it through the decoder. The decoder will have access to only these images, to only this information, and try to reconstruct the input image, right? The components of our autoencoder are the following. So we have an encoder, which creates a hidden layer containing the code that describes the input. So basically this kind of representation. In most cases, we want this representation again to be flattened, but again, you can keep it as matrices. The encoder usually shrinks down the size of the information through each layer, and the decoder increases the size. But this is not something that is constant. You can play around with it however you want. So for example, you can have an input of 20 by 20. The encoder gives you an output of 40 by 40. So this is not something that is defined, but in most cases, you want the encoder to reduce the size of your input. Some of the application areas of autoencoders and reconstruction loss that we just spoke about are, for example, domain adaptation. So in this case, what we are trying to do is we take the image, we try to reconstruct the image in this using another decoder. And of course, the rest of it with adversarial features again, adversarial training again, but at least this part of encoder decoder, you can find it in mostly any kind of paper that speaks about domain adaptation or domain generalization.
May I please go to 2 slides back, because actually, yes, may I please one more time quickly remind the difference one more time about components?
No, I think there will be more slides coming ahead that will speak about the different types of. Do you mean the different types of autoencoders or the difference between an encoder and the decoder?
No, I was aware of information from this slide. Actually, this way I lost the idea what you want to say about the components. You want to say what just we have an encoder and decoder and just like some latent space and it's all, yes?
Yeah, that's it. Yep.
Oh, okay, thank you.
Nice.
There's no more.
Encoder encodes the input into a latent space. Remember, this terminology is very useful. So basically, latent space, representation, or encoded space. And the decoder would take this code and reconstruct the input image again. Another application area would be to reconstruct corrupted images or corrupted data. So for example, here we have a noisy image, and then we try to denoise it. How do we do that? We just take the input image, we apply some noise on it, and then try to reconstruct the denoised image, right? Some of the types of autoencoders are the following. Sadly, for these values, they haven't been updated. Under complete autoencoder, so I didn't save the version on this laptop, sadly. The under complete autoencoder is the following. So basically, the input size is bigger than the latent space. There is another one which is the over complete. Hence, we have the input size smaller than the latent space. So basically, the latent space will be like this. Draw. So for example, this would be the size of the latent space. We have bigger size than the input. This could be useful to learn something, a representation that is very sparse, for example, if you need that. Basically, you take a very dense input and try to learn a sparse representation of it with a lot of zeros. That's what sparse means.
Maybe like in the Professor Dehan said, what maybe this like the bigger when the lattice space is bigger than input. In this case, maybe like where some analysis was done, maybe like with always information is significant, but like
Yes.
with like different levels of understanding, different levels of deeper analysis, like not
Exactly.
only with zeros.
So basically, we could apply more information or extract more information in it, like separate information. Maybe you could apply something that gives you, what's it called? Just like, so basically try to make each one of these features more humanly interpretable. So there are an infinite amount of things you can do. So there are smart autoencoders. Smart autoencoders try to learn a representation and force many values to be to zero, right? And there are denoising autoencoders, which we just spoke about. So basically, you have a noisy input, you send it through the encoder, and then try to decode it into its original form. The second part of autoencoders that we'll be speaking about will be variational autoencoders. So we'll be speaking about it in more detail in the, what is it called, in the lab part. But for now, variational autoencoders have the following architecture. So previously, the encoder learns one vector for the image, and then that vector is sent for the decoder and gives you the values, right? Now, the encoder is not learning your vector representation, but it's learning a vector distribution. So basically, for each feature inside the previous vector, so here, say we had 3 features here. Now in the VAE, what we will do, we will have 6 values. The first 3 values will be the mean or the centers of a Gaussian distribution, and the last 3 values will be the standard deviation of that Gaussian distribution. So it would look like this. If we try to compare variational autoencoders with autoencoders, an autoencoder would map this image to just one single value at each feature, whereas the, what is it called? Variational autoencoder would map it into a distribution based on the mean and the standard deviation of this probability. All right. Later on, what we will be doing, we will sample from this distribution one point and send it to the decoder, right? So basically, we will take an image, encode it to a set of distributions, sample a feature from all of these distributions, just one of these. Yes, basically, each one of these distributions will give you one sample, and then you will have one vector, send it to the detector, and you will reconstruct the input image. So there we go. Basically, this is 2 samples, right? So we made first sample from here, from here, from here. You see the yellow line? We made that sample. Here it is. It's a vector form. We send it through the image. Basically, that's all we will speak about in variational autoencoders. Later on, we will be speaking about what is KL divergence and all of this information, right? But for now, that's all. Segmentation. Now, for segmentation, the task is a bit different than object detection that we spoke about before, right? So for object detection, what we do is we represent an object using a what is it called? A bounding box classifier that will found the coordinates of the object inside the image and its class. Whereas now in segmentation, what we're trying to do is we're trying to attribute a pixel to every single part of that object. There are two main families of segmentations, which are semantic segmentation and instance segmentation. So in this case, you see all the human beings have the same color. So all the objects of the same class have the same color. And all the objects, so for example, here we have a table, it has another class. So basically, different objects of different classes have different colors, but objects of the same class have the same color. So basically, what we're trying to do is we're trying to predict where is person in general, where is class person inside the image. We don't care if this is an object or not. All we care about is all of these pixels belong to people. This is not very useful. What is most useful for us is the following. Instance segmentation. In this case, we classify or we predict the pixels of every object and its class. So in this case, we have this person number 1, person number 2, person number 3, person number 4, 5, and 6, and we have a table in here. So this is the difference between semantic and instance segmentation. This difference is very important, and you're going to find lots of questions basically about this later. How can we use autoencoders for segmentation? This is the question of the lecture. So what we will be doing is we will take an input image like this one. Manually, somebody will manually label this image or label the pixels of this image into either background or a human being, right? So for in this case, this is what we're interested in. So here you see that this is our map, or this is our mask that we are trying to predict. We send in the image, try to decode the mask. So this is one way of doing what? Segmentation using autoencoders. This way, is it instant segmentation or is it, what's it called? Or is it semantic segmentation? And why so?
It's semantic segmentation because two like women were like classified as just a person and it has the same color. And the background like is very
can you tell if there is a way to cleanly use autoencoders for instance segmentation? So maybe, for example, we try to predict instead of one mask, we try to predict multiple masks. Is that possible?
Due to what our like code, I think the size of the code is like limited or restricted. In this case, I think it's really hard to do this.
Exactly. So the first problem will be, depending on the number of objects, we will have different masks. And the decoder architecture does not have this flexibility of predicting different, what are they called? Different sizes for each image. This is not something that you can easily do with the deconvolutional operation, right? So the number of filters and the number of kernels is fixed. And the second thing is splitting, let's say, for example, person 1 to mask 1 and person 2 to mask 2 and person 3 to mask 3 does not give easy interpretation, right? So basically the neural network will not be able to easily understand why did this first person go to the first class, to the first mask and the second mask. And the third problem is, if, for example, we try to predict the mask where the first person is 1, 1, 1, 1, the second person is 2, 2, 2, the third person is 3, 3, 3. So basically, the neural network will not, again, be able to detect that because the neural network cannot find or cannot understand such things, right? So it cannot understand why this person was 111 and this person was 222. So this is the constraint that make it impossible to use autoencoders for instance segmentation, or at least doesn't give good results, right? The first architecture that we'll be speaking about for segmentation is called fully convolutional neural networks. So fully convolutional neural networks are the same thing as autoencoders, but they do not have any fully connected layers, right? So they're all convolutional layers or deconvolutional layers from the start to the end, right? As you can see here also, these objects are again, this architecture is again from the semantic segmentation side. Now, depending on the convolutional layers that we will be using, the results will be different, right? So here we have different versions of the algorithm. First is FCN32 stride, FCN16 stride, FCN8 stride, right? Sorry. The FCN, the 8 stride, 16 stride, and 32 stride represent the size of this final convolutional layer compared to the input. So basically, the input, the convolutional layer, the final convolutional layer that will be sent to predict the mask, will have 32 times smaller size than the input image. So you can see that when the, so let's make an example better, right? Next. So for example, the input image had 416 by 416. The FCN32 will use a feature map of size 416 divided by 32. How much is 416 divided by 32? I think it's 13 or something like that. Can you guys calculate this? Okay. 416 divided by 32 equals 13. Yep.
13, yes.
Thank you. So basically, we will be using a feature map of 13 by 13 to predict this, what is it called? This mask. And hence you can see that the mask in here is not very good. So it's definitely following the structure of the object, but it's not very accurate. And this is because we shrunk the size of the, what is it called? The feature map that we'll be using for the detection too much. FCN16S basically reduces the size of the image by 16 times, and hence it is a little bit better than the first two. And 8S, of course, is even better than 16S, but it does provide a lot more computation. So basically, you can think of this one to be at least 12 times slower than this one, and this one at least 12 times slower than this one. So basically, depending on what are the time constraints that you have, you will be using these different models. Segnet. Segnet is another architecture that is very similar to fully convolutional neural networks, and it is in fact a fully convolutional neural network. The only thing that is different is that we have something called as what is it called? Mirroring, right? So basically, this convolutional layers is the exact mirror of this deconvolutional layer. So basically, let's say the input to this one was 20 by 20 and it outputs 10 by 10. This one inputs 10 by 10 and outputs 20 by 20, right? So basically, each group is the exact same opposite in the other side. So basically, the encoder and the decoder are the opposites or the mirrors of each other. And this is the only thing that was like new in Segment, basically in the architecture of Segment.
I have a question about fully SNN.
Yes.
How's actually different from just basic encoder and decoder? I mean,
it just doesn't have any fully connected layers. You know what are fully connected layers? Like those dense layers. Exactly. It doesn't have any dense layer. So it's only convolutional neural networks. Convolutional layers, no fully connected layers.
Besides that, it's identical.
Besides that, it's the identical thing, right? It's the same thing. In here, it's exactly the same thing as fully convolutional neural networks, but in this case, we have the exact replica of the deconvolution operation or upsampling operation in the encoder and the decoder. So basically, the encoder is the map or the mirror of the encoder. UNet is exactly this, another special type of segnet. So basically, this encoder part is the same or the mirror of this decoder part. This encoder part is the mirror of this decoder part. This encoder part is the mirror of this decoder part. And this is just like the mid layer, right? What will happen in this case is the following. We will have a input image. It will be while it's going through the encoder, it will get bigger in depth and get smaller in height and width, right? So basically, we will take it like this and bring it to latent space. Now we will be doing the upsampling. When we do the deconvolution and upsampling, we will be adding the information from the, or adding the convolutional feature maps of the map or the mirror version of the encoder. So basically, this layer of the decoder will contain the information or will take the information from the previous layer and will combine it with the information from the mirror side of its encoder part, right? Same thing from here. We take this convolutional feature map, combine it with the convolutional feature map of the encoder that is mirroring of this layer, and then send it through more convolutionals and upsamples, right? So basically, a convolution, upsamples, convolutions, upsamples, convolutions, and upsamples until we try to predict this map, right? So basically, we have the same identical size of the input and the output. Mask RCNN is another architecture that we have previously spoke about. So basically, it's the same thing as, what is it called? Yes, just small question. This architecture is, again, is it instant segmentation or is it semantic segmentation?
Semantic segmentation.
Exactly. They're all the same, basically. They're all the same architecture. They're all the same model, just with a little bit more, tuning into it, right? So a little bit more information added in here. When you take the feature maps from these layers and add them to the final part of the predictions, you have more rich information. So basically, something that wasn't processed that much, more accurate or more close to the input information as possible, right?
It's semantic because it's creating space of features or what?
Semantic segmentation and instant segmentation is this.
Yes.
All objects of the same class have the same detection. So basically, you can't detect the difference between the objects of different classes. Mask RCNN, on the other hand, is a completely different one. So basically, it uses the faster RCNN architecture. First, it finds the objects, classifies them, and then in that bounding box of the object, we try to do the mask prediction, right? So basically, it's the same thing as here. We're trying to, as this part. So it's the same thing as this part, added to the faster RCNN architecture. So basically, we take the convolutional layers, upsample, apply some more convolutions, and try to find this, let's go, map, this mask of the object. For each object, we will be doing this task again and again for each object. And like this, objects of the same class will have different values or different masks.
One more time, please. What's the difference between mask RCNN and between unit? You want to say what mask RCNN just use part of a unit to just do the segmentation?
Yes, exactly. So after it detects the bounding box of the class or of the object, it performs the mask detection. So UNet does not care about where the object is in the image, right? We don't have an object region proposal network or something like that. Only thing we do is we predict the mask, right?
Right.
Whereas with faster RCNN and mask RCNN, first we find the object where it is, right? And then we ignore all the other parts, right? This is ROI pooling. We only take this part of the feature map, which correlates to only this part of the image, right? So it's basically applying UNet only on this part of the image, right?
Mm-hmm.
So every single object will have his own mask. And like this, we can differentiate between the different masks of the different objects.
With what we
I can't hear you. I can't hear you. You are muted.
what we use to create masks for objects? Some separate structure?
Yes, it's the same thing as here, right? So it's basically just more convolutions. So basically, you take a feature map, which is just a matrix, right? And then send it through more convolutions, and predict a mask. What is a mask? It's just an image. So basically, you take an image, you output an image, right? How do you do this? Just using convolutional layers. Convolutional layers take an image, give you an image. Put a lot of convolutional layers in front of each other, and then just the output, try to reduce the distance between the output that you get and the desired object map or object map.
I have a question.
Yes.
How it's deal with overlapping objects? Because like on this image, like we have two boys which overlapped, and if we predict the region for the first one,
Yes.
and when we try to predict the region for the second one, the first one anyway will take much more place in this region.
So you see that, yes, you are saying that the second person, this one in purple, is a human being inside the bounding box that is sent for mask detection, right? This is what you're saying. Is this what you're saying?
Yes. How it works.
So basically, for each object, we will take its mask alone. So we don't take the mask of human beings and send it to this mask detection part. We send the mask of every object alone and send it through this mask detection, right? So first thing is it's class specific. So basically, if you have a hand in here and a phone, it's going to be able to easily understand.
But if they are same class.
But if they are of the same class, what will happen is your object, which is in the main center or the main interest object, will contain will take the mask of that bounding box.
So like we do like a mask subtraction from like we remove a part of the purple object, and
it's not something you do manually. So basically, the neural network alone learns to detect or learns to find the mask of that specific person or the person of interest only, and not the ones in its background. And this is just happening through the training of your model. So basically, the more you train the model, the more data you have in the model, the better its performances are going to be.
Okay, I got it. Thank you.
But I want to one more time reformulate this idea. You want to say what our model will try its best to know to segment only one person in the middle, and actually, and there is a possibility what it will also mark and segment for the purple boy. Yes, it's very a percentage, but it will try to its best not to do it.
Very likely, and it will happen. It's very likely, and it will happen. This image, as you can see in here, quite perfect, right? So this was kind of generated for presenting the algorithm. Once you use the algorithm, you will find that, for example, in this case, it might take the shirt of this purple boy and consider it as person one.
Yeah, exactly. That's what I think.
This was the question, yes.
Yeah, it's not perfect, right? So it will make this mistake a lot. There's nothing stopping it from making this mistake. But if you have good data and you have a lot of data, this kind of mistakes will be reduced to a minimum.
Thank you very much. Yes, this was the best.
So how much time do we guys still have?
Like as you say, as you wanted, like this is 45 minutes, but according to the schedule, we have 1 hour and 5 minutes. is
You
you
still
to
have
choose.
5 minutes, right?
Yes,
30
officially.
minutes.
Officially, okay.
Officially, it's 1 hour and 5 minutes. Officially,
30
according to the
minutes.
schedule and the rules of 2 pairs.
хорошо. Let's take a small break of till like it becomes 0, 0. So 8:00. So 5 minutes, right? And we come back just do a quick, what is it called? A quick lab about variational autoencoders and understand their architecture and understand KL divergence again. For most of you guys, you should already be familiar with what is KL divergence, why, how is it calculated, and all of this information. But it will be nice to make this revision again, right? Because it's quite useful if you're going for research. So see you guys in 5 minutes.
Okay, see you in 5 minutes.
Minutes, okay.
Are you guys back?
Yeah.
So let's wait a little bit for the others to join. And in the meantime, I will send you the full lab link for the lab.
Can I ask a question?
Yes, of course, go ahead.
I should have asked the same question before, but now it's more clear. So
Yes.
in the last step of mask RCNN,
Yes.
the neural network will have three predictions: the class prediction, and the bounding box prediction, and the mask prediction.
Yes.
Okay, how do we match it with the ground truth? So how do we know that this prediction corresponds to this class or this bounding box, so we can calculate the loss and so on?
I didn't get. Got you. This is a great idea. This is a great question. You mean, how do we know that this box corresponds to this box inside the grant? It's basically with the intersection over union. Remember, how do we detect the box? How do we define the box? Right. So the first thing is, for the box to be defined, we use the RPN, and we define that objectness score, positive objectness score, based on the intersection over union over 70%, right? So if you have it,
okay, yes.
yes. So basically, you have the prediction, you have the ground truth. See if the overlap or the intersection over union is over 70%. In that case, we consider it to be the region of that grounding truth object, and we send it first. Before we send it, we fine tune the region, right, using the RPN, and then send it for classification and for regression, bounding box regression, and for mass detection. But this is a great question. So basically, this step is done in the first area when we are doing the region proposals and stuff like that, by intersection over union that is higher than 70.
Okay, then the question in YOLO, how do they solve this issue?
In YOLO?
Yes.
Same thing.
But in YOLO, we don't have. Okay, so you mean as so we have. Okay, yes. Yeah.
So basically, YOLO is just like, you could think of it as faster RCNN. Just let's ignoring the three scales of detection of YOLO. We can think of YOLO as just the faster RCNN, but without the second part of detection, just RPN that is doing the class of the object also. So not just whether there is an object, but whether there is an object and what is its class.
Yeah.
You got it?
Yes, thank you.
Sure. But this is a great question. Thank you. Did I share the lab with you guys?
One more time?
Did I share the lab in the channel?
Yes.
So basically, this is going to be a very simple lab. Quickly, we will pass through some code for variational autoencoders. We will speak about what they are. What is this? What is it called? The loss function that they're training on. What is reconstruction loss, and what is this KL divergence loss? Why are they added together like this to make up the final VAE loss, and all of this information, right? So to do that, I will just show you guys some articles. I'll find them here. Preferably, guys, start running the code because it will take some time to run. Nice. Guys, can you guys see this new screen now? Understanding variational autoencoders?
Yes. Mm-hmm.
Nice. So basically, this is just a couple of articles that I found on variational autoencoders. They're all very useful, and I just wanted to go through them first before going to the lab, just to show you guys what variational autoencoders are doing and how to calculate their losses. I remember that you have done this in the course of Professor Khan, and you have done the calculation or the derivation of KL divergence, and how do you do the pushing these two, what are they called? These two distributions closer together, and then you find the term that is not derivable, and you just ignore it. You only derive or reduce the part of the loss which is derivable, right? So here I just wanted to just quickly remind you guys of what are the steps, what is KL divergence, how it's done, and just seeing the code of it, right? Can somebody tell me what KL divergence is?
It's a symmetric metric.
It's a not symmetric metric. Yes, nice.
It's a difference between two distributions.
It's the difference between two distributions, but the difference is not symmetric. So basically, the difference between A and B is not the same as the difference between B and A, right? So this is a very important part of KL divergence. You guys know this already?
Seems so.
Yes, actually, yes.
Actually, yes. Did you guys forget about the lecture from Professor Khan's course? I remember that we did this, and I think that I was the one who did this lecture also. The last lecture of the course of Professor Khan.
You did a lecture for domain adaptation. Actually, you presented your idea, and one more about which one I don't know. I don't remember.
Okay, let's then go through the lecture of Professor Khan, just to remind you guys of the code. But I think this is the code. Here it is. Right. How do you represent? Right. There we go. Generative models in general. So VAE is a part of class called generative models. There are, I think, two main branches, and inside those two branches, there are two other main branches of generative models. But that's not what is interesting in our. That's not what we want to do in this case. What we want to understand is what are generative models below, right? So what is GAMS, right? This is just an example of how you train a random or an abstract generative model. Basically, you give it training data and you give it some noise, and it tries to generate new images. Variational autoencoders are a bit different than normal autoencoders because they, instead of just providing you with one latent space for each image, they provide you with a distribution of latent spaces for each image, and then you sample from that distribution. You can sample multiple times if you want, and then map those into the output image, right? You can split again the encoder and decoder into two parts. So first part is the recognition part. So this one gives you what is called the distribution of features for each image. And then there's the generative part, which is only the decoder. So later on, when we're trying to do the generation, we can just send the decoder any random noise, and he will be generating for us images from our dataset. Now let's speak about how it's done, right? So basically what we're trying to do is we're trying to learn a mapping between X into a probability space, let's call it here in Z, and then trying to learn another mapping from Z into the output. So the goal of VAE is to find the distribution Q of Z, Q of Z given X of some latent space variables, which we can sample from, to generate new samples. So the distribution here in this case, you can see Q and P. P is the distribution. So basically, just to simplify the terms later on, P is everything that is related to the decoder. Q is everything that is related to the encoder, right? Can somebody tell me if Q and P are like opposite distributions or like inverse distributions? Or are they completely unrelated? They are kind of related, right? They're doing something similar, but are they exactly the opposites of each other? So basically Q gives you Z, and basically Q takes X and he gives you Z, and P takes Z and gives you X. But are they the complete opposites of each other?
No, because we are not exactly like we're fighting by like no, we're not like complete opposite.
Exactly. They're not necessarily the opposites of each other. So they are completely different. They are different. What are they called? Distributions. They're trying to be the opposites of each other, but they're not the exact opposites of each other. Yeah, you can think of variational autoencoders as just a probabilistic spin on autoencoders. Yes, how do we should we represent our model? First, we represent the prior P of Z to be a simple Gaussian. So basically, every single feature will be the following. Every feature, we will represent it as this, as a Gaussian distribution. You can use any Gaussian distribution you want, but why did we use, you can use any distribution you want. Why did we use a Gaussian distribution? Mainly because it's simple and we can easily represent it in values, right? So basically all you need to do is the mean and the standard deviation. And like this, you can define your probability. And it's easily derivable and all of these features. And now we have the conditional P of X given Z. So this one, why can't I see my cursor? I cannot see the cursor. Now I can see. So basically, we will be trying to learn this P of X given Z, which is our decoder or our generator, which is going to be represented through a neural network. How do we train this neural network? We're trying to make P of X equals to the, what is it called? Help me.
Integral.
Yeah, the integral of P of X given Z multiplied by P of Z. Can somebody tell me what this is and what this is and why is it equal to P of X?
It's marginalization from together distribution of X and Z.
Yes. So basically what we're trying to say
Joint
is,
distribution.
yes, exactly. For what we're trying to say is we are trying to split the P of X into another distribution, which is P of Z. We're trying to make a mapping between, so instead of generating images or generating images or sampling images from the image distribution, what we're trying to do is we're sampling in another distribution and building a mapping between this new distribution into the image. So because mainly because we cannot have something called as the distribution of images, right? So P of X is not something that we can easily model. So what we're trying to model it as, we're trying to model it through a, let's call it a proxy distribution, P of Z, and trying to build a mapping between this proxy distribution, simple proxy distribution. From this simple proxy distribution, we build a mapping into an image, right? How do we build a mapping between a vector into an image? Using a decoder. So as long as we can find something that takes that sample from a distribution and maps that sample into an image, we can actually make this reasonably doable, right? The only part, the only big problem in this case is we should find this mapping through all the values of this Z, right? So basically for every value of Z, we should have a mapping image for it in the other distribution of P of x. So in order for it to be correctly or mathematically correct, we need to have it completely or fully mapping between the probability of Z, which is just something that we invented, the proxy probability, proxy distribution, into the image distribution. This is completely infeasible because first, these are like real numbers and you can't really make a mapping of every single value of these values. And if you want to compute it, it's not going to be something that is computable with the mathematics that we have so far, since this integral is going to be impossible to generate and go through all the possible values of Z. Since this cannot be fixed through a closed form loss or closed form solution, what we'll be doing is we will do the next best thing. So how can we find something that is close to this mapping, something that is similar, right? So let's think of it this way. We can only see x, but we would like to infer the characteristics of that. In other words, we would like to compute P of z given x. P of z given x. So what is P of z given x? This is your encoder function, right?
Yes.
Equals P of x given z. What is P of x given z?
Is decoder.
Decoder.
Decoder. No?
Ah, sorry. Yeah. So basically, this P of x given P of z given x is not the encoder. Sorry. Q of z given x is the encoder. So basically, this
yes,
is
it's an encoder.
Yes. This is the. Let's just put them all together here.
Reverse of encoder.
Q of z given. How do you make 6 maybe? Ah. Think of this as a line. Given x is the encoder. P of z given x is the inverse of decoder. Okay. U is what we're using to symbolize the encoder functions. P is what we're using to symbolize the decoder functions. Q of z given x is not equal to P of z given x, but we're trying to make them equal to each other, right? We're trying to bring them together, but they're not equal together, right? And here we go again with the same problem if I can see the person. This is going to take some time. Yes. Yes. So let's go back here. A little bit of math. Don't worry about the math. It's not actually that scary. It's very simple. Unfortunately, computing this P of x is, again, very difficult. So if we're trying to find this P of z given x, again, you're going to be stuck with P of x. Since P of x is this part, right? What we have seen before. The alternative is approximating P of z given x using another distribution, which is Q of z given x. So P of z given x, we said, is the inverse of the decoder. We're trying to approximate the inverse of the decoder using the encoder function. You got it? So they're not the same thing. What we're trying to do is we're trying to approximate them to be the same thing. We cannot calculate P of z given x, but we can easily calculate Q of z given x, because this is our encoder function. Of course, it's going to be a lot of calculations, but it's lots of calculations that we can do. The machine can do it easily, right? So far as yes. So basically, just remember Q is something that is related to encoder. P is related to the decoder. The first value here is the input to this distribution. The second value should be the first value is the output of this distribution. The second value is the input of this distribution. Okay.
Okay.
Nice. Now let's go to variational inference and what does it do? By approximating P of z given x using Q of z given x, where Q of Z has just a simple distribution, such as a Gaussian, we can solve this problem more tractably, right? We can make this problem easier. And how? By reducing or making these two distributions similar, or by reducing the KL divergence between these two distributions. Remember, KL divergence is like a measure or metric of this similarity between two distributions, but it's not something that is symmetric. So the KL divergence of P against Z against Q is not the same as Q against P. So let's define KL divergence between Q of Z given X with P of Z given X. So this is the formula of the KL divergence. It's equal to the sum over Z of Q Z given X log of P Z given X divided by P Z given X. So basically here, Q of Z given X multiplied by the log of Q of Z given X divided by P of Z given X. If you guys did a little bit of statistics, multiplying, summing a value with the probabilities over this, let's say, the weighted sum of the value with the probabilities is the following. So it's basically the mean of that value through this distribution, right? So again, let's do it like this. 1 over n times the sum of, I don't know, a is equal to the mean of a. Now you see this. So this is how we did the mapping from these two formulas. Nice. The log of a divided by b is equal to the log of a minus the log of b. So this so far is very simple calculations. This is simple mathematics, right? And and we have a very good law, which is called, what's the name of that guy who made this law?
Bayesian?
Newton.
Bayes law, yeah. Bayes law, I think, right. Something like that. I forgot the name of it in statistics, but the guy did us a very cool way of inversing these input and output, right? So P of Z given X equals P of X given Z multiplied by P of Z divided by P of X. So this way you can, you can describe P of Z given X without having to go through this Z given X part, just by describing P of X given Z. If you have P of Z already and P of X, then that would simplify the work for you, right? But in our case, yeah, so we apply the base rule in this place. There you go. So we end up having the following formula. Again, we have a log of something divided by something. This becomes what? A minus
subtraction.
Subtraction. So now we have the following, right? Here we go. So it's log of Q of Z given X stays the same, minus log of X given Z, plus, this is another minus from the overall here. So minus log of P given Z plus log of P given X. So far, this P given X is the decoder function. P of Z is something that we have. No, this is the distribution of the images, right? This is the distribution that we already have, that we set as distribution as the Gaussian distribution. And this is the P of X given Z, which is our distribution represented by the decoder. And this is the Q of Z given X, which is the distribution represented by our, help me out guys, by our encoder. So the only thing that we can't calculate in this area is P of X, right? Since the expectation is over Z and P of X doesn't involve, we can get it outside of the expectation. So just to simplify it a little bit here, the sum, how do we make the sum? Let's call it sum of 5 times 4 times X is equal to 4 times the sum of all the x's, right? So you understand this law.
Yes, of course.
Nice. So this is how we got the log of p of x outside. Oh shoot. Oh, shoot. Sorry. Let me try to find the cursor again. This one is going. Found it. Nice. So basically, now we have the KL divergence between the two distributions that we want to calculate as a value that we can easily compute plus something that we can't, right? Yep. Again, we simplify this further by introducing by splitting the mean on each value. And we end up having this formula. So E of Z log of Q of Z of X minus log of P of Z. Can somebody tell me what this is? So if we
I'm not sure. But
write it together, let's write it together in different way. Log of A minus log of B. What is it? So it's log of A divided by log of B. Right.
Mm-hmm.
This is equal to log of Q of Z given X divided by P of Z. Right. Sorry.
KL.
Yes. So it's log of A divided by B, right?
Mm-hmm.
What is E of Z? E of Z is the sum multiplied by P of Z. Right. No. In this case, E of Z is, as I remember, it's, let me see. Yes, here it is. So Z is from Q of Z given X. Right. This is ugly. Let's do it again. So it's the sum over Q of Z given X multiplied by the log of Q of Z given X divided by P of Z. So far you get this. How did we do the mapping from the E of Z log of Z given X minus log of P of Z, right? Do you get this? So log
Mostly
of A became log of A divided by B, and the mean over distribution became the sum over that distribution, right? Correct?
looks so, yes.
So far it's it's a little bit vague, but it's pretty simple. This computation is doable. Still can't see it. Nice. Now we can see. Yes. So here we have log of A minus log of B equals log of A divided by B, and the mean over Z equals the sum over Z. Remember, Z comes from Q of Z given X, right? So this is just simplification. So Q of Z given X multiplied by the log of Q of Z given X divided by P. This is the KL divergence of the Q of Z given X with P of Z. You get it?
Yes, of course, it's a formula.
Now, can you guys tell me what this is? So what is Q of Z given X?
It's an encoder part.
Yes. What is P of Z?
It's a simple distribution, if I understood correctly.
Yes, it's a simple distribution that we proposed for the latent variables. So it's the Gaussian distribution that we proposed.
Yes. Mm-hmm.
So this KL divergence is something that we can easily do, right?
At least calculate, yes.
Yeah, so we can calculate this KL divergence. It's calculatable. What we do is we keep log of P of X in here, and we send everything to the other side. What we get is E of Z of log of P of X given Z minus KL divergence between these two distributions plus the KL divergence between this distribution equals log of P of X. Hence, remember this formula that we were unable to understand before. P of x equals something that is uncalculatable, now became something calculatable, calculatable, uncalculatable, right? Why is this uncalculatable?
Because we don't know the distribution of x, yes?
Yes, exactly. So basically, we just, what we did is, we simplified this formula from everything is uncalculatable into calculatable parts plus uncalculatable parts. Now what we will be doing is, we will take this as the loss function and this as something that we will be ignoring, right? So the uncalculatable value that we don't know, we will ignore it. Why can we ignore it? Because it's bigger than 0. So let's imagine it the following way. We have this. This is the line. This is the final loss that we are trying to reduce, right? Let's say that this is the lower bound. This is what what we can calculate. Let's call it calculatable loss. And this is the difference between them, which is the uncalculatable loss. Let's make it in red. So this is the uncalculatable loss. What we're trying to do is, if we reduce the calculatable loss, so basically we bring the calculatable loss backwards, reduce it, that should reduce the loss in total, right? Of course, maybe it will increase the uncalculatable loss and push the loss further on, but at the same time, it's not very likely that this will happen, and the value is not going to be very influential. So let's just pray to God and hope that the uncalculatable loss would not be that much important in the calculations, and only by calculating the calculatable loss, or by reducing the calculatable loss, the overall loss should go down, right?
Yes.
So this is what we're aiming for. Of course, this is not perfect, and this is the reason why, what are they called? Variational autoencoders are still not the best generative models. It's mainly because we're not actually training them properly, and there are some parts which we are ignoring. But at least with this part, you're still able to get some acceptable behavior.
Can I ask you a question?
Yes, go ahead.
Yes, so this is, can you just repeat like these 3 terms, why each is calculatable or not? So the last one is we can't compute it.
Yes, so let's start with the ones that we can compute easily. What is it? Read it to me. Farouk, continue. So it's the mean over z of the log of p of x given z. What is p of x given z? So p is something related to the decoder, right? It takes z, gives you x. What is it?
Yes, it's the decoder part.
Exactly. So this is the decoder loss, right? So this is what we're trying to do with the. Yes. So this is the decoder loss. We can calculate it because we have the decoder, right? We have the values of the decoder. Hence, we can calculate this one over different values of z, right? So basically, we take z, some values of z, and calculate this one and just reduce it.
Okay, and how do we take z? Like we sample some random noise or something?
We sample it, yeah. We sample it from random noise, right? So basically, this is Gaussian distributions. We sample some of them and then send it to the decoder.
Okay.
Nice. Now, what is this one? The KL divergence between z, q of z given x and p of z. What is p of z?
Yes, both are Gaussian.
Yeah, both are Gaussian distributions that we can easily do. So this is the Gaussian distribution that we defined. This is the Gaussian distribution that we calculate. Remember, the output of the encoder is means and standard deviations of a Gaussian distribution. So it's something that we have. Hence, this term is calculatable. The last term, though, why is it not calculatable? Let's go back to a couple of slides earlier. So this is the P of Z given X part. Why is it not calculatable? Few slides earlier, we spoke about why P of Z given X is the following. Here's P of Z given X. The inverse of the decoder is not something that we can calculate easily. Why? Because it uses P of X as one of its values.
Okay, so
P of
like
X
just
given Z.
one question.
Yes.
So P of X given Z is the decoder network, but right?
Let's think of it slowly, right?
Okay.
P of X given Z,
given
takes
Z.
Z gives you X. So what is it? Decoder.
Okay, but I don't understand. Like, so we have like two problems. We have two approximations. We approximate P of X given Z as the decoder network, and
Yes.
why can't we just simply approximate P of Z given X as the encoder network?
It is and it is not. Remember, the encoder network is called Q of Z given X. Q of Z given X. The whole thing we're trying to do is we're trying to bring P of Z given X closer to Q of Z given X, but they're not the same thing.
Okay.
And if you make it the same thing, what will you get in this place?
0.
0. So basically, if you consider P of Z given X as Q of Z given X, you are taking away this part completely. Going back to the same thing. This is why this part is highly uncalculatable. So just a lot of problems arise when you're trying to calculate this part. So that's what they did. They tried to simplify this function as much as they can and bring the uncalculatable part separate on its own and only and make this calculatable part differentiable.
Okay, yes.
Did you get it?
Yes, thank you.
Just, I think it's very easy to go through the math. Just remember one key aspect. Q is representing something about the encoder. P represents something about the decoder, not exactly the decoder, but something about it. This will be the output of your probability. This is the input of your probability. The rest is quite simple, right? Another very cute or very important trick that you guys need to understand. Where is it? Reparameterization trick. The sampling operation is not something that is, what is it called? Differentiable, right? So how do you sample from a distribution? You just make a random value from that distribution, right? So usually this is just an algorithm that we do. We try to map it from the normal distribution and then do this sampling, right? So this is an algorithm, handmade. It's not something that is function, which is differentiable. So what we do is, instead of sampling from the output of the encoder, we sample from some distribution, from a normal distribution, completely separate normal distribution, and then convert that value into the distribution that we got from our model, right? So how do we do that? Can somebody tell me the parameter? What is it called? The reparameterization trick in simpler terms, right? Let's. How do you go from n of mu and sigma into n of 0, 1? How do you do this?
Normalize.
Normalization.
We normalize. So let's say it was z minus m divided by s. This was x. How do you go from z into x? Okay, let's keep it here. So yes, we said z minus m divided by s. How do we go from Z equals to something related with X?
Multiply by STD and plus min.
Nice. So what is it called? X times S divided by minus
Plus.
Nice. So basically the Z is what we want. The Z is sampled from this N of M of S, and the X is sampled from N of 0 and 1. What we do is we sample from this N0, 1, we get the X, then we just do this simple calculation and get the Z. Now, the value of Z is differentiable with regards to S and M, right?
Yes.
Previously, if we just got Z just like this from sampling from N of M of S, then this sampling operation is not differentiable with regards to M and S. This reparameterization trick allows you to get a value that is differentiable with regards to the parameters of your distribution without sampling from this distribution. So basically, we sample from another distribution and then map it into the distribution that we want. This is the reparameterization trick.
Okay, but in this case, we still sample from outside distribution, but this distribution of means equal to 0 and SD equal to 1, but it was acceptable.
Yes. That's it. That's the main part that I wanted you guys to just remember. Now let's go to the code and try to read this part, right? So the code is pretty simple, very basic stuff. Just some hyperparameters, useless. Reading the data. Again, you already are familiar with this part, right?
Imad?
Yes?
Can you show the code because you don't see?
Thank you. Forgot. So now you can see the code?
Yes.
Thank you for telling me. So again, the first part of the code is just some imports, a little bit of defining the hyperparameters, learning rate, and stuff like that. And here we have just defining our data loaders, transforms, and just useless stuff, right? So this is not something specific to variational autoencoders. Now let's start defining the architecture of our model. So the architecture of the encoder is the following. We have some convolutional neural networks, and then we have a fully convolutional, fully connected neural network that will give us the mu. So here it has the space, the space is the same thing as the latent dimensions, right? So basically here we have the output of the encoder equals to 2 times latent space, right? Sorry. This is the output of the encoder. We have the mu and we have the variance, and it will give you 2 times the latent space size, right? Each one of these contains latent space size. Later on, what we will be doing is simply we calculate, we send the X, the image, to some convolutional neural networks, we flatten it, and then send it through a fully connected layer to give us the centers. We send it through a fully convolutional layer to give us the standard deviations, and then we return these two values. So this is the output of the encoder. So far, it's simple. So far, it's not something that is difficult. Remember, we can return as many values from our neural network as we want. And we can just send X directly. So this is not something that is sequential, you see. So X goes through this, then goes through this one, and you have two outputs, right? The decoder function is even simpler. So basically it takes, so here are the definitions of this thingy. So basically we have a first linear layer that takes latent space and gives you some output, right? So this output will be later on converted into just a convolutional or matrix, right? That will be sent through a convolutional transpose 2D. So convolutional transpose 2D, I think we should have a session where we speak about different, what are they called? Classification architectures, ResNet and VGG and all of these friends. So basically their architectures, what are their components, why are they good? And we should include also stuff in it like so conv, transpose, and upsampling, and all of these things. Do you guys think it's useful?
Yes.
I'm not sure. Maybe
short
yes,
term-
but I'm not sure.
These fields are very easy. We can just Google them.
Yeah, I think you can, everything you can find it on Google. To be honest, it's all the courses like a Googleable course. But it will be very useful for all of you guys to understand what convolutional transpose is in calculation. But so far, what we can understand it as just the opposite of a convolutional layer. So basically, it takes a small size and gives you a bigger size. The forward function is simple. We take latent space. So this x is in fact the, let's call it the z, the latent space, right? So this is the output image. The variational autoencoder, just as a whole, is the following. We have components is encoder and decoder, right? So these are the two components of it. The forward function is you send it through the encoder, send the input image through the encoder, you get the mean and standard deviation. You make a sampling from this mean and standard deviation through the following algorithm, remember? So basically we sample from yeah, so basically here it is. EPS equals torchlight standard deviation normal. So basically here it is. So basically we sample from a normal distribution. Here is EPS, multiply it by standard deviation, and we add to it the mu. What is mu? The mean, right? Then we add to it
mean.
Yes, exactly. So following the same architecture or the same formula that we just spoke about in the lecture, right? There are two steps here. For example, here in the training, we do the sampling. If it's inference, then we just directly send the mu, right? This is the most probable value that we will be getting. Now that we have the latent space, we simply send it through the decoder and we get the reconstructed X. The output would be reconstruction, latent mu, latent log var, just so we can use them later on for calculating the losses.
Can you just repeat why do we return mu only in the?
Yeah, simple. Let's think of it. Now we're sampling from a distribution like this. What is the most probable value you will sample from?
Yes, it's mu, but
so this is the only reason that they use this one. So basically, outside of the training, instead of sampling and risking to get something very high, like let's draw it again, sampling and you risk to get something from the tail, right?
Yes. Okay.
To remove this risk, so basically you always get something in the mu area, so that the reconstructions are always as good as possible.
Yes. Okay. I have another question. Why do we, instead of outputting the standard deviation, why do we output the log of the standard deviation?
This is just for simplifying the calculations.
Oh, okay.
Yeah, this is just a trick. Remember, for example, for the output of the neural network, sometimes we send it through the log, right? So, for example, instead of sending it through, instead of outputting it directly and sending it through the loss function, we send it through the log and then send it to the loss function. So this is just a trick to simplify the calculations later on, just to speed up the loss function later on. This is just a trick. You don't have to worry about this. Did you get it?
Okay, got it. Thank you.
Now the VAE loss, again, it's a very simple loss. So basically, it's the cross entropy between reconstructions and the X, simple one. So basically, reducing the difference between X and the reconstruction of X. You can use another loss, for example, MSE or anything that you want, but binary cross entropy gave better results, right? Now the KL divergence. This one is equal to minus 0.5 times torch sum of 1 plus log var minus mu power of 2 minus the log var of exponential x, what is it called? The log var xp, right? So basically this one is variance or standard deviation. Let's call it standard deviation, S. This is mu to the power of 2, mu squared. And this is the log of the variance and plus 1. If we go back to the, what is it called? To the, let me share again. Did I close it? Yes, I did close it. We go back to the lecture and we will see the following. Here it is. Yes.
You're not sharing the screen.
There it is. So this is just the closed form solution of KL divergence. Remember, KL divergence is the sum over the first probability times the log of the second of the first probability divided by the second probability. This is the solution of it. When you have both both functions as Gaussian distributions, you just simplify them a little bit and you get this function. So it's half times the trace of this sigma, this covariance matrix, inverse of this covariance matrix multiplied by this covariance matrix. So it's just a little bit of calculation. This is just two ugly calculations. Once you simplify it, it will become the following. Yes. Yes. Once we simplify it, it will become the following. So this is 0.5 times the sum. So this is the sum just to go through all the samples of 1 plus the 1 is the first part of the equation that we just saw before, because it's they're all, what are they called? All the matrices are just
diagonal.
Diagonal matrices for the variances. And here we have the log var multiplied minus mu power 2 minus the standard deviation, right? So this is just the calculations of the KL divergence between two different normal distributions. And then the final loss would be the reconstruction loss plus this beta parameter. So this is just the balancing parameter between the KL divergence and the reconstruction loss. And this is basically our loss of the VA. We create the variational autoencoder, we send it through the CUDA, and we create our trainer. Let me find, we create our optimizer using the parameters. We give it the learning rate, we give it the weight decay. We start the training. This is just to get the losses, right? To remember the losses. For every batch in the image, you see how we don't take the data into account, the labels into account. You basically take the image batch, send it to the image, send it to the GPU, send the image through our VAE component, and it returns to us the reconstructed image, the mu's or the centers of the distributions of every sample, and this is the variances of the distributions of every sample. We send them to calculate our loss function, which is the sum over, or the weighted sum over the reconstruction loss and the KL divergence. Remember, zero grad, this is just to make sure that no previous calculations of gradients were made. We calculate the back propagation or gradients, and then we just make a step. This is just for visualization purposes, right? Now we can see how the average reconstruction error is going down. So here we have the first epoch was very high, and then it continues going down again and again. It doesn't really go down that much. You can train a little bit more, but overall, this is the training curve of the loss function. Yep, so alternatively, we can just load a pre-trained VAE without having to train it manually. So this was a well-trained model. Yep, so this is the error of that well-trained model. And there we go. We're trying to reconstruct these input images. So you can see that the reconstructions are not perfect. So for example, the 5 is awfully reconstructed. The 7 is awfully reconstructed, but the 7 is reconstructed as a 9. The 5 is reconstructed as a 0. Here, all of these reconstructions are a bit, they're not always the same number that you give it, mainly because what is it called? The reconstruction, we'll see it a bit later on. So here, you can see this is the two-dimensional space of the reconstructions. If we start with a value, let's say around 300, the reconstructions of that value would be 8s, right? If we increase a little bit the values, we will start getting 3s. We increase them a little bit more, we start getting 2s. We increase them getting more a little bit, we get 0s. So this is how the latent space actually looks like, or how the latent space is being mapped, right?
Can you repeat how did you get this image? The last one.
Yes, so this is the 2D latent space. So basically, we take some values in here. Say, for example, let's make a matrix together. Here's a matrix, right? And let's put here 0. Sorry. Here we put 0. And no, let's put 0 here. Here we put 0. Here we put 100. Here we put 100 on another axis, right? So this is the VAE with only two features, right? You got it? So basically, our encoder outputs only 2 features. Let's see the values that we are outputting, right? If our encoder outputs a point in here, so this is the latent space point that was outputted by our model, which corresponds to 3. And let's say here it's 2, right? So these are the values that were given to us by our encoder. Okay.
So these are the muse and signal?
No, these are the muse only. Remember, with inference, we don't care about the signal. We care only about the muse.
Okay.
So these are the muse of the feature that we got from the encoder. What we do is we take this point, send it through the decoder, and replace it in this matrix with the graph or with the image that we got from the decoder. So this image, this image of a 1 corresponds to a value that was given of 50 and 300 or something like that, right? So we gave the decoder values 50 with 300, and he gave us the value of 1. And we created this kind of map that you can walk through the classes inside the latent space. So basically, here is the 0. You go in this feature direction. You go from 0 to 5 to 8 to 9s. And basically, this is what's happening. So 7s, 9s again, 3, 2, 6, you see? So now you are walking inside the latent space. You got it?
Yes.
You understood how this image is being formed?
Yes, yes.
Yeah, so basically we create line space, right, of the latent variables. We get the latent variables, send them to the GPU, send them to our decoder, and then plot the images according to these values of the latent spaces that generated. Хорошо? Хорошо?
Yes, got it.
Nice. Good. So this is why you can see that the output of, we gave it a 5, but the output was 0. And that's because in the latent space, 5 is very close to 0. So if you inputted 5 and the latent and the variable or the value that you outputted from the encoder was closer in this range, it will be decoded as a 0. You understood why there are these differences between the original image class and the variational autoencoder reconstruction.
Yes, yes.
Хорошо. So basically, this is the lab. The goal of the lab was just to explain to you guys what is variational autoencoder, how is the loss being derived, what are the terms that were just completely ignored from the loss since they are not computable, what are the terms that we got, and just to see this example of how an encoder looks like and having multiple outputs from our neural network.
May I one more time, like you mentioned at the beginning of the lab, what you view like pay special attention to the losses. Why you have two losses? Why we one loss are weighted? May you please one more time go for it? About the losses.
About the losses, why are they weighted here?
Yes, why we weighted? Why we have two? Like one time. Yes.
Yes, simple. Remember, KL divergence is not the loss that we are reducing. Let's go back to the lecture. Here. You see, KL divergence is not the only loss we have. We also have this one. So this is the reconstruction loss. This is the KL divergence.
And we count them both, yes?
Yeah, and we do them both in order to reduce this final or total loss of our model, of our VAE. You got it?
Yes, thank you very much.
Why do we why do we what is it called? Why do we weigh them and not just add them together? It's because the ranges of these values are not the same. So here, in this case, we have variational beta equals to 1. If you want to, for example, try and focus more on reconstruction and getting more accurate reconstruction, you should make the variational beta equal to, for example, 0.2. In this case, your reconstructions will be more clear, but your generation ability will be less clean, right? So basically, if you reconstruct a 9, it will always be a 9, but if you want to generate other types of 9s, it will not be as good. So this is what you can do with your, what is it called? Variational beta in here. You can play around with it and specify what you would like to focus more on. Whether you would like to focus on keeping the same class of the input image as the reconstructed ones or as the generated one, or we'd like to just be able to generate as much as possible, regardless of the class. Did you get it?
Yes, thank you.
Do you guys have any questions about this?
No.
Nice. For tomorrow, again, tomorrow will be a very will not be any lectures. Tomorrow will be just focused and dedicated to your final projects. Please try to find some ideas. Try to prepare your reports in the structure that was described in the PDF or in the document, the doc document that I shared, and try to at least have it filled or have it structured. And tomorrow we will be writing it together, so you will be able to submit it by tomorrow, and at least you get the first part of the grade of the final project. At least everybody should get that part of the grade of the project.
Can I ask a question? It's a bit general. I see variational autoencoders used in so many like applications. So where are they used other than generative models? So do they have?
They're not used in generative models, to be honest. They're used as feature extractors.
Oh, okay.
Yes. So remember in the first part of the lecture, I gave you an example of domain generalization, right? Of domain adaptation.
Yes.
That's a very good part where you need this concept of mapping an image to a, what is it called? A vector form. And variational autoencoders provide you more flexibility than autoencoders. So basically you can just have more creativity with what you want to do.
Okay.
Imad, I have a question.
Yes, go ahead.
When we reconstruct an image, how do we compare it with the original one? Like we don't we have a loss function here.
Yes,
but
we
how the
compare it pixel by
comparison
pixel.
works? What?
We compare it pixel by pixel. So we have, yeah, so pixel by pixel. So basically we have an input image, reconstructed image. We go through each one of these pixels and compute the loss between them and then just sum it.
I have another question.
Yes.
It is not related to variational autoencoders.
Yeah.
It is related to CNN.
Yes.
So when we back propagate, we know we can change weights till flatten layer. But
Yeah.
how do we change our kernels? Like on what basis? Because we already calculated their outputs.
Yes. So the TNNs weights. Remember the convolutional operation. Remember, it's
Yeah.
not that complicated. In fact, it's just multiplication and addition. So if you abstract away the fact that we are sliding it through the image, just abstract away because this is just text, right? The derivations that will be calculated only care about the fact that we are applying multiplication and addition.
Mm-hmm.
So basically, in the final class, the kernel weights will be trained in the same way that the weights of a fully connected neural network are being trained. So it's the same kind of propagation, but in this time, since you have multiple times of calculations against the same number, then this adds a little bit more complexity just because of the sum, basically. But it's not really that different. So it's just the same thing as the fully connected layers, the same kind of training.
Okay, thank you.
You're welcome.
Okay, thank you, Matt. See you.
Have a good day. Have a good night.
Thank you a lot.
Good night.
Good night.
So about tomorrow, we will not
Thank
have
you.
lecture as it's supposed to be like a lecture, but we will discuss our project, yeah?
Yes, only for us.
And
And
it will start as usual at 10:20.
Yes, it will start at 10:20. Yep.
Okay, no problem.
we
And
can,
see you tomorrow.
Thank you, and see you tomorrow.
Thank you.
yeah, I haven't selected any project. I can select it tomorrow, yeah?
Yeah, tomorrow we will select together.
Okay, thank you.
See you. Bye bye.